All right. Well, looks like we missed class because of snow. Very exciting. So I am putting this lecture on Unit 4 on Angel for you to review so we can keep up and not miss any time during the snow break. The next unit, Unit 4, is on two chapters, Chapter 6 and Chapter 9. I will be talking about Chapter 6 on this first section, which is how bone is formed. We've already seen and identified the bones in the body. Now we're going to discuss what's the physiology, how they actually get made. It's pretty exciting. We'll see how it goes. Remember that this is our second system. Our first system was the integumentary, and we dealt with all the parts that make up that system, all the organs. Well, that's the same with the skeletal system. When you think of the skeletal system, you think of just bones, but really there's a lot more to it than just bones. You have the cartilage between the bones. You have the ligaments that hold bones in a certain position. You also have the surrounding connective tissue that helps support and provide nutrients for the bones and stimulate growth. So there's a big piece of the puzzle here that we're going to have to add to our understanding of the skeletal system. In fact, the next unit, part of the next unit is, or the next chapter, is dealing with how bones interact together, articulations or joints. So this is kind of the building block for that. There's a lot of words here. Hopefully you're not going to try to copy all of them down. We already know the function of the skeletal system. We've talked about this briefly before when you did your little list of what each system does. But let's just briefly go over them. You know that the main purpose of bones is to support underlying tissues. For instance, the rib cage really protects and supports the organs underneath. They're connected to it, right? And we also know that bones have the ability to store fat, and blood cell production happens in there in the bone marrow. That's significantly important. One of the interesting things is physics, the physics of bone interaction. It's interesting to know that the way the bones are shaped and they interact are specific to the function that they will provide. In other words, your arm, when you look at your arm at your elbow, it's only allowed to move a certain direction. But that particular movement gives you a mechanical advantage when picking things up. We'll get more to that when we talk about levers, but that's the idea. You know, if you pick something up, they say to bend your knees, right? Well, the fact that you can bend your knees there is a physics advantage using the ideas of levers. So we'll talk about that. So you've also noticed that bones aren't all the same shape. I mean, when you think of bone, you probably think of this long bone here, and that's typically what most people think of when you think of bones. But, you know, you have the bones in your hand, the flat bones in your skull, then you got these crazy shaped bones in your vertebrae, and just all kinds of different shaped bones. And the significance of this is that even though you have these cells that make bone, the way in which the bone is made and the shape and when it starts and stops and how it's remodeled is pretty significant, right? If you change the shape of the femur, let's say, its ability to withstand all of this weight that is being put on it changes significantly. So the shape is extremely important. So let's just look at the parts of a bone. Specifically, we'll look at a long bone. This long bone here, you notice that the area up here and most of this area, the same down here, has this spongy looking bone. As you get to the outer edge, it's more compact. Even around here, the outer edge is compact bone. So the outer edge is compact, where the middle is more spongy. The ends of the bone are more spongy as well. In fact, if you look at the center of this particular example, it's hollow. The middle or the shaft is hollow. So let's label the parts of a long bone. The ends are called the epiphysis. That's the epiphysis. And the middle is called the diaphysis, or the shaft. Now in between the diaphysis and the epiphysis is this little area called the metaphysis. And these labelings are significant when you talk about bone formation, not only in early development, but as you go from birth to around age 25. So now let's go to what we always do with most of our organ systems, is talk about the organs and how they're specifically made. That means we're going to talk about the tissue. The tissue, when we talk about bone formation, is osseous tissue. Now we know that it's a connective tissue. Recall back to Unit 2 when we talked about the different types of connective tissue, and one of them was supporting connective tissue, and specifically bone. So we can say that because bone is a connective tissue, it has both a matrix and specialized cells. Now you remember a matrix is made up of organic and inorganic compounds. In this case, the inorganic components of bone are what makes it hard, solid. We call that the hydroxyapatite. That's now these little chemical formulas look a little scary, but they're just illustrating the ingredients that make this hydroxyapatite. It's really calcium phosphate and calcium hydroxide. These two combine together to make the hardening, the mineral deposits of the bone. Now you notice that there's a lot of calcium, right? That's the main ingredient. Hence we say you need calcium for your bones to be structurally sound. And that's true. It is a very important ingredient. Now we'll talk about the significance of calcium in a little bit, but it's more than just for bones. Just remember that. So how do we make this tissue? That's the interesting part. It's made by these specialized cells. Hey, that's part of being a connective tissue. So what are these specialized cells? Well, we briefly went over these. If you recall, we said that there's these immature, early development bone cells called osteoblasts. Then there's the maintenance cells, the ones that maintain the bone that you've made. They're called the osteocytes. Now, osteocytes, we know that are located in these regions called lacunae, where they are stationed and able to provide maintenance of the bone that is formed around them. Then we have these weird cells called osteoclasts, and they dissolve bone. That's just pretty interesting. Let's take a look at each of these cell types. First, we look at the osteoblast. Now, you notice here that these are grouped cells represented by the blue arrows, pointing to the blue arrows. Now, what they're doing is they're secreting that hydroxyapatite, which is hardening the matrix around them. So this is actually bone here being formed. All this. Now, what's going to happen is they're going to surround themselves with bone. So these osteoblasts are going to start laying down bone, and eventually it's going to surround themselves, and then they will become osteocytes. So look here. On the edge, you see that these are osteoblasts. And here's a good example. You know, it's starting to lay down this matrix, but it's going to surround itself, like this one did here. Now, what do you think this cell is going to become? That's right, it's going to become an osteocyte. And now it's sitting in the lacunae, and it's going to be the maintenance cell for the bone that's surrounding it. So we form it with the osteoblast, we maintain it with the osteocytes. Then we add in the scrubby bubbles. Remember I told you about the scrubby bubbles, that commercial with the bubbles that eat grease? Well, these particular scrubby bubbles don't eat grease, they eat bone. The enzymes they secrete actually dissolve bone. That hydroxyapatite is going to be dissolved. Now that sounds very interesting. So these scrubby bubbles really dissolve bone. The enzymes they release are going to break down that hardened matrix into its simplest form, which will be the calcium and the phosphate. And it does two things. it helps shape the bone. Think about, you got one side that's making the bone and one side that's breaking it down. Those two things work together to give the bone its shape. Just like I had mentioned before, a potter who's making a pot of clay puts a whole bunch of clay down first, like the osteoblast, and then starts to take some away to make the shape they desire. That's the osteoclast. So this is very similar. But the other function of osteoclast is not just to shape the bone, but let's say the amount of calcium in your blood is too low. Where could you get the calcium from? Well, probably the biggest place you store it, which is in your bones. So since calcium is more important than just for bones, these osteoclasts will be stimulated to break bone down to provide calcium for the blood. And all of the other organ systems that use calcium will be able to have the calcium they need. So, an interesting component of the bone cells are where they come from. You recall that when the sperm meets the egg, those cells divide, and you get 4 cells and then 8 cells, and then those cells become specialized. Well, what we're talking about is these original stem cells are going to divide into something more specialized. The example here is this mesenchymal cell. So a mesenchymal cell is a generic stem cell. We will see that it is involved in making fibroblasts, chondroblasts, all kinds of general stem cells. Well, it's also responsible for making the osteoprogenitor or osteochondral progenitor cells. The osteoprogenitor cells are going to produce osteoblasts. So let's quickly review that. So that the origin of an osteoblast, you would say, starts with a mesenchymal cell, which differentiates into an osteoprogenitor cell, which will give you your osteoblast. Now, the osteoclast comes from a different type of origin stem cell. And that kind of makes sense since it does the complete opposite of what the osteoblast does. And in particular, the osteoclast comes from the hemocytoblast. So the stem cell origin of an osteoclast is a hemocytoblast. And that's the same stem cell that will make other blood cells, specifically immune cells, which some of them, like the macrophage, eats up stuff, right? Eats up bacteria, phagocytosis. Well, it's going to be a good cell to make an osteoclast, which will eat bone. So here's a little diagram of the origin of these two important cells in bone formation. So the mesenchymal cell is the origin of the osteoblast, where the hemocytoblast, or the hemopoietic cell, is the origin of the osteoclast. Don't worry that they're different names. You can just remember one of them. It's fine. Here's a question. What is the origin of an osteocyte? I'll give you a second to think about that. Since it's one of the cells that we said were important in bone development, it would be a good idea to know what's the origin of an osteocyte. So I'm humming the Jeopardy theme right now. Silently. Okay. So what'd you think? The origin of an osteocyte is an osteoblast. Recall that we said osteoblasts form bone. They harden the matrix around them, and then they mature into osteocytes in lacunae. So the origin of an osteocyte is an osteoblast. And the origin of an osteoblast is the mesenchymal stem cell. So, why do we care about all these things? Well, because of that H word that we love, right? Homeostasis. Homeostasis is the reason why we care about the integumentary system. It's the reason why we care about the skeletal system and all the systems that we talk about. This homeostasis is the body's ability to balance, providing the needs inside with the ever-changing outside, right? So, what is homeostasis with respect to the skeletal system? Well, we know that that bones need to be structurally sound, since that's a few of their main functions require the bones to be structurally sound. So these cells that we discussed help maintain the bone structure, keeping them solid. We also know that we expose bones to a variety of stresses. Let's say when you jump off the stair, or when you're exercising, right? Your bones are exposed to impact. And if your bones aren't able to respond to that, they could break, right? If it's chronic. So bones need to be able to respond to exercise or stresses. Also, we said, equally as important is the body's need for calcium. So these cells help provide a way to store calcium and remove it and put it into the blood when necessary. So really these cells are quite essential in more than just the functions of the skeletal system. Other organs depend on the skeletal system as well. So let's look at the microscopic view of bone. Now we're going to be doing this in lab. So we have a model that looks just like this one here, a little bit more detailed than this one. And we'll be able to look at both the spongy bone and the compact bone. So where my pointer is around right now, this is all compact bone, and then this is spongy. You notice there's a significant difference in the appearance alone of these two types of bone. And what you see here is kind of interesting. You notice the compact bone has these rings, right, in which bone is organized. Now, the significance is, look what these rings are surrounding. They're surrounding blood vessels. That kind of makes sense, right? Because bone is hard. So you wonder, how do you get nutrients to those poor osteocytes that are in the lacunae? Right? So you got to be close to a blood vessel. And when bone is formed, it forms around, if I can get this, or maybe I can get a pen here. So you notice that these arteries and veins are surrounded by bone. So when bone is formed here, it's going to form around these vessels, these blood vessels. So on the outside, we have the periosteum and those osteoblasts, and they're laying down bone. But as they get deeper into the compact bone, they're going to start surrounding blood vessels because they're going to need to get nutrients. That still doesn't answer all the questions of how do you get nutrients to diffuse through a solid piece of bone, right? That's a pretty good question. The other question is, this spongy bone looks significantly different. It doesn't quite have rings. It almost looks like a jelly roll. You ever seen those? Jelly rolls where they put jelly on a piece of cake and then they roll it up. That's kind of what this looks like. Started off and rolled and rolled and rolled and rolled. It's not as eloquently organized as the compact bone, but it's similar. So we'll take a look at both of these. Okay, so compact bone first. Well, the name implies the bone is laid very close to each other. They're connected to each other with these different arrangement of these bone layers. So we have these bone layers that are surrounding the compact bone. They're called circumferential because they're surrounding, right? Like circumference. Then we have these circles, these rings around the arteries. They're called what kind of lamellae? Concentric, right? Concentric circles around one circle next to the other. And then you have interstitial lamellae that holds it all together, right? So there's not a lot of space here without bone, is the point. And you notice that it's highly vascular. You ever break a bone? Let's see if I can get the pen here. You notice that, look at all these blood vessels. You got some here, you got some here, and all through the bone. So imagine if you take and you damage the bone, it's going to bleed significantly. But it needs to have nutrients throughout, and these vessels throughout the bone to provide the nutrients. So let's talk about the names of these parts. Well, the rings have names. They're called lamellae. Lamellae. The central cavity is called the central canal. Isn't that nice? So you have a central canal surrounded by lamellae, rings of bone, concentric rings of bone. And then you have these little spaces here, these lacunae with osteocytes in them. But if you look closely, you see like these little lines. You see little lines here that are within the lamellae. Now those are the really interesting things. They're actually grooves. So imagine if the nutrients from the center here are trying to get out to the edge. They can pass through these grooves. They're called canaliculi to get to the cells to provide nutrients so the cells can maintain the bone that's around them. So if you were asked by your buddy Bob, how do nutrients diffuse to the osteocytes in compact bone? You would say, Bob, well, they go from the central canal through the canaliculi in the lamellae to each osteocyte in lacunae. Sounded pretty good, didn't it? But you have to make sense of all that, don't you? Here's an even better picture. So here's the central canal, and here's the circles are the lamellae, and then these little divots, these little indentations, are the lacunae. What you don't see here are the canaliculi really well, but you look over here, you see all these lines coming out within the lamellae are all canaliculi. They're all these little grooves to provide a way for the nutrients to diffuse from the central canal to the osteocytes. So how does spongy bone differ? Well, it also needs nutrients, right? They kind of show it here, if I can get a pen again. Kind of show it here. Right here, you see this artery and vein? Well, imagine there's a bunch of them flowing through here. You notice that there's space in between these trabeculae, they're called, the arms of spongy bone. All these the web that's made, this is all trabeculae. So if you were asked, how is spongy bone organized, you would say, well, it has lamellae, and it is arranged in such a way that it forms these arms, these webs, called trabeculae. Another thing you notice is this red covering here. It's very thin. This is the endosteum. Whereas the compact bone was surrounded by the periosteum, right here, we'll just highlight it. Spongy bone is surrounded by an endosteum, both connective tissue layers. We'll get into what they do specifically. But the fact that there's so much space between these trabeculae allows for a lot of blood vessels and bone marrow to reside. And that makes sense. If bone marrow is forming the blood cells, you better have a lot of blood vessels nearby to pick up those blood cells that it's making, right? Okay, so I'm back. I was talking about spongy bone and the necessary arrangement that allows for blood vessels to go and flow through and bone marrow. Okay, so now we're moving on to the coverings of the bone. Remember we said that both the compact outside of a bone has a covering and the inside, spongy bone, has a covering. They're different. They have similarities, but they have some differences too. So let's look at the outside, the outer covering of bone, represented here by this area here. This is called the periosteum. Now, these cells, you can see some little nuclei here. These are osteoblasts. They're also fibroblasts. They got lots of different types of tissues. Fibroblasts for the connective fibrous layer on the outside here. And osteoblasts to provide a way to make bone from the outside in. We know what kind of bone formation that is. We'll talk about it later. If you recall, oppositional growth versus interstitial. We'll get back to that later. Then the inside of bone, the spongy part here, is lined by the endosteum, which is a very thin layer that's broken up, right? It's not as consistently thick as this periosteum is. And it's got these osteoclasts. Remember what they do? They'll eat bone. So we're mainly forming it from the outside, and if we need to take some bone away, we'll take it away from the inside. Now that makes sense, especially if we're trying to change the level of calcium in the blood, well, let's dissolve the matrix here so the blood vessels are close, the calcium can move right into the blood, diffuse right in there. Okay, so two different coverings of bone, the outside periosteum, the inside endosteum. Two different functions. Oh, look, here's an osteoprogenitor cell. Do you recall what that does? I'm pausing for you to say the answer. What you know? It makes osteoblasts. So we can also make bone from the inside. Okay. So periosteum, we said, has an outer fibrous layer and an inner cellular layer. So the entire bone, so a long bone, is covered except the areas that articulate together. In other words, where the joint happens. So one part of a bone that interacts with another bone, that area is not covered by the periosteum. It'll be covered by cartilage because of the interaction from one bone to another. So the periosteum is not found on the ends of long bones where they interact, or inside of joint capsules like in the knee or the shoulder, which I'm very aware of, by the way. So what is the purpose of the periosteum? Well, think about what's surrounding bone. You had bones in your hands, right? They're rough. They're not smooth. They have certainly the ability to generate friction, right? So imagine all the soft tissue that's around it. Let's say a muscle is contracting next to a bone and it rubs up against it. That would not be good, right? That would damage the muscle. So this periosteum provides a softer, more soft tissue boundary between the hard bone and the surrounding soft tissue organs. Also, the periosteum provides a way for nutrients to surround the bone. So not only do you have blood vessels going through the bone as it's formed, but you have a constant supply of blood around the bone through the periosteum. That means bones are highly vascular, right? That's why it's not such a great idea to break them. The third function of the periosteum is to provide a way for bones to grow. So, for instance, remember I said, jumping off the stairs or some stresses that the bone is exposed to, it needs to respond. And the way it responds is by growing, getting stronger. So the next time that you do those things, it's more able to withstand that stress. The periosteum is a site of growth. Also, if you break a bone and you tear the periosteum, that's the first thing that gets repaired, because it'll be able to lay down bone below it to repair the area that was broken. The endosteum has a different layer of functioning. Yes, bone growth and repair are part of its job. If you break a bone through the entire layer, it's going to have to help repair it from the inside, right? The inner portion, the cavity, or the spongy bone portion. But even more so, it's the area where we can provide an avenue to take the calcium out of the bone and put it into the blood. So that's a really important part. You'll notice that whereas the periosteum that's around the bone is a complete layer, the membranous tissue within the spongy bone, the endosteum, is an incomplete cell layer. It's not connected, doesn't have that fibrous outer layer. It's just a single layer of varying cells. We have osteoblast. That's these little guys here, all these little guys. We have osteoclast, and we have osteoprogenitor cells. Okay. So now we're going to talk about the way bone is developed during embryological development or embryonic development. In other words, when you're in mom's belly. Remember, we said that all connective tissue comes from mesenchymal cells. Aside from, can you recall what cells that are involved in tissue physiology, development? do not come from mesenchymal cells? That's right, the osteoclast. The osteoclast does not come from a mesenchymal stem cell. It comes from a hemocytoblast, or a hemopoietic stem cell. So the mesenchymal cells are going to have to differentiate into osteoprogenitor cells. But not all of them, right? Because some of them are going to be part of the membranous, the fibrous tissue. So it has a dual role. One is going to make the periosteum, and the other one is going to provide the osteoblast to start making the bone. So when would you start to see kind of a skeletal framework? We're not necessarily saying bone, but we're saying the framework. It kind of looks like the skeleton. Well, that's within the 6th week of conception. You can start to see an outline of the skeleton, which is really cool. It looks very cool. We say that it's not bone yet, it's cartilage. So imagine we have two sources of making bone. We have this membranous mesenchymal source, and then we have this bony skeleton. That's really cartilage, right? So kind of wrap your brain around that. It's kind of hard to imagine that if the body is, if the developing embryo is making bone, what are the two ways it's making bone? Well, one is from the mesenchymal cells specializing into bone-forming cells, and the other one is from a cartilage framework. So we're going to have to figure out how both of those work. How can you go from mesenchymal cells to making bone? And what kind of bone would you make? Then how do you go from the cartilage frame to bone? And what kind of bone would you make? Okay, so those are the two questions that we're asking ourselves. How do we go from a membranous mesenchymal origin to bone? And what kind of bone would it be? And how do you go from a cartilage framework to bone? And what kind of bone would you make? Okay. Well, both of these bone formations, we said start around the 6th week, and they stop around age 25. So if you're 25 or older, you're probably not growing anymore because you're not making more bone. We'll get to that shortly too. Okay, so two ways in which we make bone. We said one is from a membrane and one is from cartilage. Well, guess what the names are? You'll like this. The one that's coming from a membrane, the mesenchymal cells, is intramembranous ossification. Right? Ossification means turning tissue into bone. The other type of bone formation that's from cartilage is endochondral. So from the inside of cartilage, you're going to make bone. So it's endo, inside, chondral, cartilage ossification. Isn't that cool? So now we know intramembranous, membrane, endochondral, cartilage. So we're going to look at the steps in which we can get from the mesenchymal stem cells that are forming membranes to bone, and what kind of bone. And then from the cartilage frame to bone. Okay. Both of these types of bone development involve the process of calcification. That's the cells depositing that hydroxyapatite, which hardens the matrix. Okay. So, our first one, intramembranous ossification. Around the 5th week of development, you start to form bone through this process. And this ends around the 2nd year. So this isn't going to form those bones that continue to grow throughout your lifespan of 25 years. Right? Because after that, your growth is no longer. You're not getting any taller after 25. Around 25, I should say. It does vary slightly between individuals. Okay, so how are we getting the bone? Well, it's actually from the connective tissue membranes that are formed during development. You start to make bone. Wait till you see it. It's quite interesting. It's very dynamic, as you'll see. So where are we getting this bone from? Well, we know. With osteoblast. right? They're going to make the bone. And what kinds of bone are they going to make? Well, they're going to make flat bones, like the ones in the skull or the mandible or the clavicle. That's the kind of bones that are produced from the osteoblasts that are provided through intramembranous ossification. So let's take a look. So you got to get your bearings here. You kind of got to have an idea of where you are in the body. All of these blue cells right here, these blue ones right here. Let me get the pen. The pen again. All these blue ones right here are mesenchymal cells, undifferentiated mesenchymal cells. Some of them are starting to form membranes, while some of them right here, what do you think these blue ones are? All these blue cells surrounding, you can see them really nicely here. What do you think these are? These are osteoblasts. Where do they come from? They came from the mesenchymal cells. So that's what they're trying to show you here. These cells in the middle here, these right here, are mesenchymal cells. And they differentiate into osteoblasts. Now you notice that these osteoblasts are doing something to the matrix, because this clear matrix here is for membranous tissue. That's what it started as, right? Membranous tissue, hence intramembranous ossification. But now the matrix is very different here, isn't it? It's significantly different. It's less transparent. It's very dense. And it looks like it has some cells that it's surrounding. So let's see if you can give me an idea of what's going on here. These osteoblasts are doing what to the matrix around them? They're hardening it. This is bone. And they're surrounding themselves as they do this. So what would you call this guy right here? This would be an osteocyte in a lacunae. Isn't that neat, right? Now I want you to notice something. This right here, as it's labeled better than I'm circling it, is a blood vessel. This is the really cool part. This isn't just random bone laying down. This bone is being laid down, and this arm is extending out. We call this arm a spicule. What do you think it's extending out to do? It's going to wrap itself around this blood vessel. You can see it already happened here. So this part right here was a spicule, right? And then it wrapped itself around that blood vessel. Now that blood vessel is trapped. But what's it going to do? It's going to provide nutrients to all these osteocytes and lacunae. Pretty cool, huh? So you'll notice that there is a stepwise process in intramembranous ossification. It would be a good idea for you to go through the steps, but make sense of it. Don't just memorize the steps. Think about what's happening in each step. Mesenchymal cells start to combine together and they differentiate into osteoblasts, right? They're all stuck together and they're going to make osteoblasts. Then they start to ossify or harden the matrix around them, right? Step 2 says it's not just hardening in a random area, it's making these spicules which will trap and surround blood vessels, right? And then step 3, over time, now you get this bony structure. What do you think these things are called? Do you recall? These are trabeculae. And what are they surrounding? They're surrounding vessels, blood vessels. So now look down here. Look what you get. You get these spongy bone trabeculae, right? With a small, thin, compact border. So most of this bone is spongy. It's a flat bone from the skull, which is what kind of bone intramembranous ossification makes. Okay, so you have two goals here. One is to understand what's happening during intramembranous ossification and what kind of bone it makes. Right? Those are the things you want to get out of this. You got to know the steps. You got to know what's happening in the steps and the significance of those. Okay. Now we move on to the second type of ossification, endochondral. This one it starts from cartilage, but you could say what? Where does cartilage cells come from? We know this. They come from mesenchymal cells, right? Because we know that connective tissue cells' origin is from mesenchymal cells. But the difference is that these mesenchymal cells don't directly differentiate into osteoblast. They're going to differentiate into cartilage-making cells. They're going to form this hyaline cartilage framework. This is the category where we get into the different types of bone growth, the oppositional and the interstitial growth. Right? The oppositional is the bone gets thicker in diameter, whereas interstitial is it gets longer. So we'll talk about both of those later on. So let's talk about endochondral ossification. So look here. Going back. Getting a pen. This right here, this is all, hard to do without a mouse. It ain't pretty. But you get the idea. This whole thing here is cartilage. Now imagine if you were looking at a developing embryo in mom's belly, you would see a bunch of these cartilage frames in what looks like a skeleton. It'd be very basic, non-detailed, but it would be the framework of a skeleton. But it would be all out of cartilage. Very flexible, right? So what we're looking at now is how this process takes you from a cartilage frame to bone, and what kind of bone do you get. So let's look at this process. The first thing you see is that the center of this cartilage, the chondrocytes in the center, they're changing. Something's happening to them. They're getting really large. Really large. You can see here, this is trying to show you that these puppies are getting large. So as they're getting larger, they're getting, their nutrient demand goes up, doesn't it? They're going to need more nutrients. In fact, they get so large that some of them even rupture. And when they rupture, they leave behind a cavity, right? There's no longer cartilage in there. So that's the first step, is that these chondrocytes in the center of the cartilage frame get large. They enlarge and they die. But step 2 shows you what happens as a result of this mass increase in size of the chondrocyte. Their nutrient demand goes up. They attract blood vessels, right? Because low nutrients is going to attract the nutrient provider, right? Which is the blood vessel. So these blood vessels are attracted to this cartilage framework. And in fact, soon we'll see that they're so attracted they're going to poke through and get to the center. They haven't done that yet. They're just close to it now. Now, an interesting fact here, the bone that's being formed here, you see it represented by the yellow, is the beginning part of the periosteum. Remember, the periosteum has 2 layers. What are they? They're the fibrous layer and the cellular layer. The cellular layer is where the osteoblasts are, and they're starting to form bone here on the outer edge, just barely. So on step 2, you have the blood vessels being attracted here, and you're starting to form the periosteum and some bone. Right, originally you were surrounded by the perichondrium, right? Remember that? The connective tissue layer that surrounds cartilage. That's still here. But now it's being converted to the periosteum via the conversion to osteoblast. Now look at it. Step 3, what happened to that nutrient artery? It poked through, didn't it? Why? Because of the nutrient demand. Well, when it pokes through, it's bringing in fibroblasts and osteoblasts. So the center of this bone now has got nutrients, and it's also got fibroblasts and osteoblasts. What are the osteoblasts going to do? They're going to start making bone. Look, you can see it. We call this the primary ossification center. Right? The primary center of ossification, the primary place where we're making bone. Now, what do you notice? I would argue that not only are you making bone, but you're also doing what? You're also breaking it down. You're remodeling it. Now that's confirmed by looking at step 4. Look what happened. We got a big hole here. We still have bone, right? We're going to have spongy bone here and then compact bone on the outside. This is making what part of the bone? Do you recall? You can see what's the beginning of the diaphysis. And then this would be the epiphysis, right? And the metaphysis. So we're starting to see the parts of a long bone. So what kind of bone do you think endochondral ossification makes? Long bone. Very good. So we got our cavity here. But notice it's highly vascular. And there's going to be bone marrow in here, right? Okay, so let's look. Next, step 5. Now, what do you think happened to the chondrocytes on the epiphyseal ends? They got larger, right? Their nutrient demand increased. So now you got blood vessels poking inside there. And they're bringing in osteoblasts and fibroblasts and osteoclasts. So now, these are called the secondary ossification centers. That kind of makes sense, right? And they're going to make the ends of the long bone. But I want you to notice something in step 6. Okay, yeah, we started to make bone here and bone here. But this blue stuff is all still what? It's still cartilage. Now this should make sense. The ends of long bones have cartilage on them. We said that because they interact with other bones. That's the articular, where they articulate with other bones. So we call this the articular cartilage. That's going to be what this is here. That's where it comes from. But now why would you keep cartilage here? Okay, fine, it makes sense to keep cartilage on the end here. But why keep cartilage here? What is this epiphyseal cartilage going to be for? Well, it's how we grow. Think about it. We said that the periosteum is going to provide a way for bones to get thicker, oppositional growth. But we also need interstitial growth for bones to get longer. Well, this cartilage that's remaining behind can continue to lay down bone so that the bone gets longer. But as you approach age 25, what do you think is going to happen to this epiphyseal cartilage? It's going to fuse this bone and this bone together and no longer be cartilage. Look at this x-ray. If anyone who's over 25 goes to the hospital and this is their x-ray over here, let's get the pen back. If this is their x-ray, right, this one over here, look at this stuff. That's not good. That looks really bad, right? You get a serious fracture on what end of the end of what bone? What bone is this here? It's the radius. How do I know? Because it's thumb side. So that would be a serious fracture on your radius. But this is not an alarming x-ray, right? Even though it looks like there's a lot of fractures all around here. These aren't fractures. These are the epiphyseal cartilages. So this means that this bone is still growing. And look at the space between all the carpals. They're still growing. Now, compare that to this x-ray. Well, now, you see this line here? Right? There's a line here now where there used to be what looks like space. It's really just cartilage. Growth has stopped here. This is now the epiphyseal line. So you notice that there are lines all over the place here. This is showing you where growth is no longer occurring. Look how tightly packed the carpals are now. Right? So now growth has stopped here. Okay. Now, I'm going to ask you a question. This one back here was an example of what type of growth? I'm not asking you endochondral or intramembranous, right? We know that this is endochondral because it's making the long bones. I'm asking you, is it oppositional or interstitial growth? That's right, it's interstitial. This one is oppositional growth. This is from the periosteum, right? It's laying down bone underneath. Whoops. Now I want you to notice something. The periosteum is laying down bone into these lamellae, as we talked about before. How is it going to do it? Well, here's a nice artery. You'll notice the steps. Look what it's doing. It's laying it around that artery so it traps it. What do you think this is going to become? this is going to become the central canal. And then the lamellae are going to be laid around it. And then you're going to have these canaliculi that this nutrient artery is now going to provide for the osteocytes that you matured into. So oppositional growth has to be around the blood vessel in order to sustain that bone. So you'll notice that as bone grows thicker in diameter, it's growing around these nutrient arteries. Pretty cool, huh? I think so. Okay, so now that you've made this long bone, why is it so important that the shape be the way it is? So this is an example of what bone? Femur, that's right, it is the femur. So here's the femur, and you notice that it has a large head, a very thick neck, and then a long shaft that goes to a large base. Why this shape? Well, you remember that the femur's location is just below the entire trunk and arms and head of the person. So all of the weight of those areas, the trunk, the arms, and the head, are all being applied, that force is being applied to this bone. And the way it's shaped here, the force will be distributed throughout the length instead of in one area. That's significant, right? If you change the shape, let's say your neck is a little bit longer. Now instead of the force gradually coming over here, it's going to take a harder turn. That means the head is going to be under greater stress. So that means any impact, let's say jumping off a stair, you could break the neck. So you need the neck to be a certain length. You need to be the head to be. So all this shape is extremely important. Now, let's say it's the perfect shape, but you're constantly jumping off of things. Sorry about that. What's going to happen? You're going to remodel based on the applied force, right? You're going to be thicker in one area, thicker down here maybe. So if you look at the bones of a lineman versus a wide receiver, you would notice that the thickness regions of the bone are going to be in different areas because of the stress that they're put under. Not to mention the difference in size, right? But just even factoring out the difference in size, the areas that are larger are going to be in different areas, which is pretty cool. So bone formation is dynamic in respect to the stresses that you put it under. Also, this is probably these are macro vessels, right? You can see, look over here, you can see some micro vessels. How vascular is bone? Extremely vascular. Imagine if you break this bone here. You're going to have a significant amount of blood loss, right? So you need a quick repair of the vessels when a bone breaks. One of the things they're concerned about when you break a bone is blood clotting, like one of those clots breaking off and entering into the bloodstream and getting stuck somewhere because bone is so vascular. Why do you need bone to be so vascular? Well, it is dynamic. We said it's growing. It needs nutrients. But also, there's two things you have to remember. Recall that bone is is a storage site for calcium, right? But it's only a storage site if it can get it to the place where you need it when you need it. Where do you need it? In blood, right? Blood is what delivers nutrients to different organs. So if different organs need calcium and bone is where you store it, you're going to need a high vascular region to get the calcium from the bone to the other organs. So that's one reason. The other reason is, what's inside this cavity? This marrow cavity is bone marrow. And what does bone marrow do? It makes bone cells. Bone cells. Blood cells. That's what I meant. It makes blood cells. Well, blood cells need to be where? In the blood. So, hence the vascularity. Okay, so you got two good reasons to be highly vascular. Okay. What are the different major arteries that supply bone? We have the nutrient artery, the one in the center of the diaphysis. Then you have the metaphyseal vessel. That's the ones on the ends of the bone. Right, you see that here, right? Here's the metaphyseal artery. Here's the nutrient artery. But you also need arteries in the periosteum. That's the periosteal artery. So you got three major sources of blood to a bone. The periosteal, That's this one here. And this one, right? Periosteal arteries, the metaphyseal arteries, and the nutrient artery, right? Those are the three main sources of blood vessels in bone. That's not the only thing that's in bone. So if you smack your bone, does it hurt? Yes. So you have sensory nerves in your bone. Why? Well, because your bone doesn't want to get broken. It doesn't want to have permanent damage. So the way it communicates when the stress is too much is if these nerves are triggered, right? These sensory nerves are triggered, then there's too much pressure, there's too much stress. And that goes to your brain and says, hey, that hurts. Stop it. Why do you need lymphatic vessels? Well, when you do have inflammation and damage, there's excess fluid. If you keep that fluid around, that can cause a problem, right? So this lymphatic vessels help drain the excess fluid. They also provide, that's right, immune cells, right? Immune cells. Okay. So we said, bone is constantly changing. Now, I use the example of exercise. Yes, certain types of exercise, specifically high-impact exercise. Now, typically that gets a bum rap, right? That high-impact exercise. But what they found in the research is, if you want to increase bone density, it has to be high impact. Things like jumping rope or just jumping. Just the fact that you're landing on the bone gives you more of the entire bone increases in density. Exercising with weights, so lifting weights, resistance exercise, has shown to increase bone density, but only in the area that's pulled on by the muscle. So it's more local change. If you want the whole bone to change, you're going to have to do some sort of impact exercise. But what else stimulates bone to grow? Well, is there a difference between a 7-year-old and a 12-year-old? Think about that summer, right? When your friends came back from the summer and they're like 6 inches taller, you're like, what the heck happened to you? Their bones just had a rapid stimulation to grow, didn't they? Well, that's hormonal, right? Growth hormone and thyroxine and other hormones stimulate bone growth. And so it's also regulated by hormonal changes. We said that there's a stimulus to break down or store bone based on calcium levels, right? That's controlled by hormones as well, calcitonin and parathyroid hormone, or as it's abbreviated in the slide here, is PTH. All right, so let's talk about this calcium thing since it's so important. Calcium level maintenance is extremely important. I'll tell you why. I've said it before, but let me remind you. Your nerves can't send impulses, which is what their job is, without calcium. Your heart can't beat without calcium. Your muscles can't contract without calcium. Your digestive system, all these other systems need calcium. So how much calcium is in your blood is extremely important to maintain. If that gets too low, many systems are affected. So it's highly regulated. So now let me ask you this question. If calcium levels are too low in the blood, what would you want to do to bone? Would you want to store bone, make bone, or would you want to break it down? Let me ask the question again. If calcium levels in the blood are too low, what would you want to do with bone? Would you want to make bone, or would you want to break bone down? That's right. Break bone down. Because bone is made up of calcium, right? That's how we store it. We store it in that hydroxyapatite. So, one of these hormones is going to stimulate bone to be broken down. And what cell is it going to stimulate to do that? That's right, the osteoclast. The osteoclast is the one that breaks bone down. So one of these hormones is going to stimulate osteoclast when blood calcium levels are too low. The other one, what do you think it's going to do? When blood calcium levels are too high, which is also dangerous, it's going to want to store that calcium in bone. So it's going to stimulate bone formation. And how is it going to do that? By increasing what bone cell activity? That's right, osteoblasts. So let's take a look at these guys. So here's the problem. Calcium ion concentration is below normal. So what happens? Well, parathyroid hormone is released, and it does three things. Look here. Well, with the bone, it stimulates osteoclast activity to break down more bone and get more calcium into the blood. Okay. Parathyroid hormone also tells the kidney, hey, don't get rid of calcium. Keep it. Don't pee it out. Keep it. It also tells your small intestine, hey, whatever calcium is consumed, absorb it. A lot of it. Increase your absorption of calcium. These three things together are going to help bring calcium levels in the blood back to normal. So if blood calcium levels are too low, what hormone is secreted? That's right, PTH, parathyroid hormone. And what does parathyroid hormone do to increase blood calcium levels? It stimulates osteoclast activity, breaking bone down, getting calcium from that. It stimulates the kidneys to retain calcium, keep it in the body. And it stimulates the small intestine to absorb as much calcium as it can. Okay. I just wanted to see if something. So what's the opposite of this? If blood calcium levels are too high, right? So the hormone that is involved in that is calcitonin. Calcitonin. What do you think it's going to do? It's going to stimulate osteoblast activity to take the calcium from the blood and put it in bone. It's going to tell the kidney to secrete more calcium. It's going to tell the small intestine to absorb less. So calcitonin does the opposite of parathyroid. Okay, good. So we know that there are other vitamins that are essential for bone formation. Vitamins C, A, K, and B12. There's a chart. You can look at the different hormones, what they do. We've discussed them. But I always like charts, right? Tables. Okay. All right, here. Types of fractures. I just like looking at these, right? Not so much anymore since I have one, but still, they're interesting. You can look at the descriptions and discern the differences in fractures, right? You can see this one. Green stick. You ever taken a young tree and try to break the branch? It doesn't. It really is flexible, but then all of a sudden it starts to peel off if you squeeze it close. That's what a green stick fracture is, right? It's peeled off a part of the bone right here. Epiphyseal fracture. These are bad news. You know what? Let me tell you a story about these. Football for kids. Back in the day, it used to be age. So certain ages played together. But they were finding that there was a lot of injuries. And in fact, a broken bone at the epiphyseal plate, what do you think happens? It stunts growth. That's right. So they realized that some 10-year-olds were bigger than other 10-year-olds. And, the force equals mass times acceleration, right? They had a lot of mass, so they could generate a lot of force. So now youth football is based on weight, right? So that's a better way to reduce the risk of this. So look at these fractures and just kind of understand the description. There's a few of them here. Not so pretty. My brother-in-law had something like this, but at his wrist. Not good. Okay, so how do you repair a fracture? Well, you can imagine, right? When you break a bone, it's bloody. Very bloody. Right? It's filled up with a blood hematoma, right? Fracture hematoma. What's going to happen to that blood? Well, it's going to be replaced by cartilage and bone, right? So you get an internal callus, like a swelling. Blood vessels are going to come in and be repaired, right? You see the repairing of the blood vessel here? And you're going to start to form solid bone, right? Compact bone on the edge, spongy bone in the middle. What you notice here, even after it's repaired, there's evidence, isn't there? You have an external callus. An orthopedic surgeon can notice a break from years and years ago, Um, what about this question? Do you think that the bone is weaker there now? The answer is no. In fact, some argue that it could be stronger. The bone is great at repairing itself. It is not more susceptible to a break after it's been broken. Now, multiple breaks in a bone, that's a different story, but a clean break, it can repair quite nicely. No other serious problems with that. Now we look at some effects when bone formation has gone bad or just getting old, right? Look at the difference between these two bones. Now they're taken on the similar magnifications. You notice this one looks very holy. Yeah, this is osteoporosis. It's when bone becomes less dense, becomes brittle. A lot of things can cause this. It could be diet, just the effect of aging. But it also is hormonally influenced. Think about who's at higher risk for osteoporosis. It's females. One of the ways that calcium is absorbed is based on the hormonal levels of estrogen and progesterone. And that changes significantly during menopause, right, and postmenopause. And that influences the calcium reabsorption, which decreases. So there are a lot of factors that can cause that. Bones get thinner and weaker as you get older. Women lose about 8% of bone per decade, men 3%. That's a lot. Doesn't seem like a lot, but it's a lot. What happens with bone loss? Well, you get shorter, right? You've noticed this. You lose your teeth. You have fragile limbs. Think about if you and I fall, we just get a bruise. But someone who is older, they can break a hip, right, for the same fall. I put some diseases here for you to look up. Just take a gander at what's on the slides: osteoporosis, hormone effects, cancer. This is a good slide to know, right? We talked about all this: exercise and diet and menopause, but just make sure that you're keeping an eye on this. This is some language that you should become familiar with. These are key terms. If you took medical terminology, you recognize all these things. But these are common terms used to discuss dysfunction in bone, right? Osteopenia versus osteoporosis, and all the way down the list, osteoblastoma, cool stuff. All right, that's it for Chapter 6. We'll come back and do Chapter 9.